Hello students. Let me begin with something you've surely noticed. Have you ever tried pulling a heavy trolley? If you pull gently, it moves a little. If you pull harder, it goes farther. This is a perfect example of how work is measured in physics. It depends on how much force you apply and how far the object moves. In physics, we say that work depends on two factors. 1, the force applied, and 2, the displacement caused by that force in its direction. So here's the basic rule. More force or more displacement means more work. We express this with a simple formula. Work equals force multiplied by displacement in the direction of the force. Or in short, W equals F into S. Let's now look at the most basic case, when a constant force acts on a body and the body moves in the same direction as the force. Suppose a force F moves a body from point A to point B, and the displacement is S. Then the work done is W equals F into S. Here, W is work done in joules, F is force in newtons, S is displacement in meters. This is the simplest case, and it only applies when force and displacement are in the same straight line. But what if the direction of force and displacement are not the same? For example, suppose you pull a suitcase along a slanted path. The force is applied at an angle, but the suitcase moves horizontally. In such cases, we need to resolve either the force or the displacement. There are two valid methods. Method 1. We take the component of displacement along the direction of force. That gives us W equals F into S into cosine theta, where theta is the angle between the force and displacement. Method 2. We take the component of force in the direction of displacement. So again, W equals F into cosine theta into S. Both methods give the same result. It's all about projecting one vector onto the direction of the other. You'll see both cases shown clearly in figures 2.4 and 2.5. Let's now derive this important formula step by step. Suppose the displacement vector makes an angle theta with the direction of force. From geometry, the component of displacement in the direction of force is S multiplied by cosine theta. So the work done becomes W equals F multiplied by open bracket S into cosine theta close bracket. That simplifies to W equals F into S into cosine theta. Alternatively, if we resolve the force instead, the component of force in the direction of displacement is F multiplied by cosine theta. So work becomes W equals F into cosine theta into S. Either way, the final expression is W equals F into S into cosine theta. This shows how angle between force and displacement affects the amount of work done. Now let's explore special scenarios. Case 1, positive work. This happens when force and displacement are in the same direction. So, theta equals 0 degrees and cosine 0 equals 1. Thus, W equals F into S. Example, when a falling object moves under gravity, both force and displacement are downward. You can see this in figure 2.6. The work done by gravity is positive. Case 2, 0 work. If displacement is perpendicular to force, theta equals 90 degrees, and cosine 90 equals 0, so W equals 0. Example, centripetal force in circular motion. The force is towards the center, while the displacement is along the circular path. Shown in figure 2.7, the work done by the centripetal force is 0. Case 3, negative work. If displacement is opposite to force, theta equals 180 degrees. Cosine 180 is minus 1, so W equals negative F into S. Example, when you lift a load against gravity, the force due to gravity is downward, while displacement is upward. Gravity does negative work. You'll see this clearly in figure 2.8. Now, how do we measure work when force is not constant? That's where graphs help us. If we plot a force versus displacement graph, the area under the graph gives us the work done. If force is constant, the graph is a straight line parallel to the x-axis. Then work done equals area under the graph equals force into displacement. If the graph forms a triangle, work equals half into base into height is equals 1/2 into F into S. This is beautifully shown in Figure 2.9, where the shaded triangle gives us the work done by a variable force. This method is very helpful in nonlinear systems like springs or rockets. Let's quickly revise what we've explored about measuring work in physics. Work is the product of force and displacement in the direction of the force. General formula, W equals F into S into cosine theta. Work is positive when force and displacement are in same direction, 0 when they're perpendicular, and negative when force opposes displacement. For varying force, work is the area under the force-displacement graph